All right. All right, so let's start. We have Ryan Jones from Infleqtion. He will be talking about their efforts in QHPC integration. I'll hand it off to Ryan. Go ahead, please.
Great. Thanks so much, Amir, for inviting me to talk about some of our quantum HPC work here at Infleqtion. My name is Ryan. I'm a principal embedded systems engineer. I'm also one of Infleqtion's earliest engineers. And right now I'm predominantly focused on our control software and hardware architectures for quantum computing. I'll say for my talk here, feel free to raise your hand to interrupt or drop some notes in the chat. I'll be trying to watch that so that if there's a particular topic you're interested in, we can address your questions or comments while it's fresh on everyone's mind. And so to get started here, let me talk a little bit about Infleqtion. So Infleqtion's core focus is neutral atom technology. And so this includes our core neutral atom cells. And so these are targeted for research, academia, and industry. And we use that core technology to build applications like position, navigation, and timing, or different sensing applications like inertial sensing. The same core technology also extends to quantum computing. And here at Infleqtion, we develop quantum computers, and we also develop quantum software and algorithms. So Infleqtion is a global company. We have offices in the US, the UK, Australia, and systems deployed with collaborators across the world and beyond. As you can see at the International Space Station. And so to just show some of the things we've deployed, on the left here, we have a few of our quantum computers that we have delivered to our collaborators. The top left is one that we delivered to the UK at the NQCC. The one just below that is for Japan's Moonshot project. In the middle here, we have some PNT systems deployed to both the sea and the sky here. And then on the right, we have some of our space applications. The astronaut here, Christina Koch, you might recognize. She was on Artemis 2, but here she is working on Infleqtion's Cold Atom Lab on the International Space Station in 2020. And so, getting to sort of the heart of it, and what I think you all are most interested in is probably our quantum computing efforts at Infleqtion. And so to the left, you can see our QPU rendering of our quantum processing unit, a whole bunch of optics and fancy lasers and systems. And we have at the heart of this is a vacuum cell, and that's can have cesium or rubidium atoms or some combination of the two. And so the way that we manipulate these atoms is with laser beams or magnetic fields, E-field, microwave radiation. We can do things like physically move them around, change their energy state. And so our claim is that neutral atoms are nature's perfect qubits. And so they have a natural advantage in that they're very uniform and stable, long lasting. I think that's referring to our coherence times. It's commercially scalable in that for us to double the amount of physical qubits we have is relatively very low effort compared to, say, another modality. We can sort of just put a little bit more laser power on there and change our mask and trap more atoms. And we also have longer coherence times. And so there's a few reasons that might be interesting to this group. One is that we can have deeper circuits potentially, but also that means that for us, we have more relaxed requirements for things like online decoders. So we would love to have a sub microsecond latency round trip decoder run that's great, but also our modality can tolerate worse performance than that. And we have a lot of different ways that we can control our system, a lot of different knobs to turn. And we also have universal connectivity, any-to-any or all-to-all qubit coupling. And that last one in particular, I think will be interesting for this group because I think it might expose an edge of how users might interact with our system versus another one. And so the feature that I'm spotlighting here is dynamic reconfiguration. On the left side here, we have, just for reference, I've got just a photo of one of our scaled arrays. So this is 1,600 sites, well over 1,000 physical qubits. And on the right, we see some examples of atom reconfiguration, where we're actually taking these individual atoms and shuffling them around, moving them in between atoms, and bringing them to some target location. And so we can prepare our array so that we're ready to execute some particular quantum circuit. But one of the more interesting things is that we can also reconfigure the array while we're executing the circuit. And so that's one of the things that allows for general all-to-all connectivity. And I'll elaborate on that here a little bit. So this is interesting for this group, I think, because all-to-all connectivity gives us a few choices for how we might handle fault-tolerant operations. And so here in this animation and the circuit here, we have a fault-tolerant state preparation operation. And this is just one that I picked out because it was, you could sort of see what was going on a little bit easier. It wasn't getting too complicated. When we see this purple box, it's doing some 2-qubit operation on these neighboring atoms. And once we get to the end of the chain here, we can actually physically pick up that qubit and move it over to a different area and do another 2-qubit operation. And that can allow us to do a quantum information. We can forward that quantum information in a way. And so for any quantum computer, we might do something where we would take a measurement of the ANSIA qubit and then send that off to some classical system, and it would do some decoding and apply some correction. That would come back and we'd actually apply those corrections and keep moving. But for inflection systems, our all-to-all connectivity means that we can do forms of measurement-free quantum error correction. We can do coherent feedback. And so for end users of someone on the openQSE stack, while they can use their normal circuit tools, they should be aware of our system's capabilities, our all-to-all configuration, how to hint to the compiler to do this these sort of motion operations, and have some understanding of what the costs are, right? Because it may sometimes be appropriate to do that, to actually take a measurement and then ship that data off to a classical decoder and incur that latency penalty. Sometimes that might be a better option for depending on what the overall cost is as we're moving to maybe very, very large circuits. And so just a high-level overview of our quantum computing stack. So at the top, we have the application layer. And so this is where someone comes to us and says, we have this problem that we would like to solve. And we use some algorithms we've developed or co-develop some new algorithms or work with our collaborators to find some sort of way to exploit the target system to find a solution. And so usually right now, there are people in the loop for this. I think there's hope that eventually software stacks will handle a lot of this tooling for us. Right now, this is very much a person in the loop. And so we have teams and software stacks that are working at this higher level and working directly with collaborators, such as with the Oak Ridge Quantum Science Center. So the software to our interface, the interface software to our hardware systems is called SuperStack. And so we would typically take in a universal quantum gate set as an input in a big circuit and transpile that down to our native gate set via our SuperStack middleware. And that would compile down to pulse sequences that we can actually execute on our control system to execute our desired quantum circuit. Right, and so a little bit about SuperStack. So that is the interface, the main interface to our system that we expose to users, but it's also useful quantum compiler tooling in its own right. And so in 2022, Infleqtion acquired SuperTech and has continued development of SuperStack, which is sort of their flagship software program. It's very much a write once, target all philosophy. And so you could build your own quantum circuit in any of your usual suspect languages, your Qiskits or your Circs, and SuperStack will optimize that either for some sort of application or maybe for some particular target. So unsurprisingly, SuperStack has an optimized backend for Infleqtion's neutral atom quantum computers, but it also has optimized backends for other third-party systems like IBM. We have optimized backends for some trapped ion, some other superconducting, and some spin qubit systems as well. And so if you're interested, there's some interesting application highlights in our Read the Docs, and you could learn more about what this tooling does on its own. And so let's discuss some of our hybrid workflows here. And so for right now, I'm just going to lump sort of all of these into one of two categories. And so I'll define batch time workflows to mean a workflow where we submit one circuit or a collection of circuits, and eventually it spits out a whole bunch of measurements, and the classical system can figure out what to do next. And so this is the period of this loop is very long. It's 10 minutes, or it could be hours. I mean, really, it could be longer. It could be, it's not really bound to days, weeks, months. The real-time workflow is a little bit different, and that's where the classical system is actually in the loop with the quantum computer. And so the quantum computer would partially execute a circuit or execute a sub-circuit, send a measurement out to that classical system, and then often that system would send some sort of operations back, some sort of probably pretty low-level instruction operations with, here are some things that we want you to do. And so the period for this sort of loop is much shorter. This would maybe be on the order of a millisecond, probably including the classical and quantum durations. Okay, and I've just got a question, and so I will look at that. So I assume your compiler is able to work with openQASM also. And so yes, SuperStack is compatible with openQASM. I think there are some limitations, but it's largely I believe we're not feature complete with openQASM, but that we can support openQASM. And so, can you give an example of the real-time workflow? I will get to that in just a moment. I think first I'm just going to touch on our batch time classical quantum workflows. And so here's our slow workflows that I guess probably many of you are already pretty familiar with, but it's an interesting application. So here's a batch time application for precision oncology. And so this is some ongoing work that we are doing with the University of Chicago and MIT for Wellcome Leap's Q4Bio. So over here, we have a bunch of patient samples. We pre-process that data, and then we frame this as a PCBO tournament, which is a polynomial constrained binary optimization tournament. And so The quantum computer helps identify what sort of features and relationships look the most important. The classical computer takes that information and progressively narrows down the problem. And so eventually we just smash down all these degrees of freedom until it's just something that the classical computer can just solve itself. This is a classically intractable problem, but this is an application where a quantum computer could make an intractable problem tractable for a classical system. And so in the end, we get a set of informative biomarkers that could be useful to classify patients into meaningful clinical categories. So, and maybe if I went over it too fast, so here's like the batch time tournament. Here's where it's perfectly fine that these sort of they were just sort of going back and forth. There's if the systems are not co-located, it would almost probably not mean anything to the end user who's running classical algorithms and quantum algorithms that are each taking tens of minutes and going back and forth. Things like co-location don't matter at all at these durations. And so I'll move on to some of our real-time workflows. And so unlike our batch time hybrid workflows, which any sort of external user or collaborator would be able to use and implement in any way that they would like to, the real-time hybrid workflows are currently something that we only use internally. I still wanted to speak to them though, because I think that it is worth thinking about how we could standardize heterogeneous real-time computing in some way in the future that would allow us to have more flexibility, allow the end user to define interesting classical operations that are in the loop of the quantum computer. And so start just a bit about our real-time hardware. We have a bunch of programmable system on chips, and they're predominantly doing things like orchestrating all the peripherals and modulating laser beams and acquiring a bunch of measurement data and just measuring this or managing the overall state of the QPU. And so they're distributed across this high-speed topology, which I have here on sort of the left side. And some of these links are super fast. They're in like the 400 gigabit per second territory for some of them. And so we also have a ROS link, which I think that many people here will be familiar, but that's remote direct memory access over converged Ethernet. And that's linked to expand our real-time compute capabilities. And so one of the interfaces we've been focusing on here is GPU, the little mom and pop outfit called NVIDIA. And while I have a GPU here, I think that this sort of ROS paradigm is very flexible, and there's no reason that in principle we couldn't extend this across the HPC spectrum, where it could be FPGA clusters, it could be TPU, MPU, DPU, CPU, any of the PUs, and on the other end of that. And so I think that there's maybe some way that we could define some way to have this seam that multiple vendors could use the same tooling. And so with that sort of hardware in mind, I wanted to discuss a little bit about the heterogeneous kernel. And so to the left, I have some quantum instruction, just sort of pseudocode, where these first two lines here, we're executing some quantum operations. And then we have a measurement command. And then we take that measurement data and we pass it off to some decode function. And that's some classical decode function that presumably is defined just above here in some pseudo language. And it's fully classical. And when we compile this down, this actually compiles down into several executables that we can run on classical machines. And so the RT CPU, the real-time CPU, will play back sort of these appropriate pulse sequences that make sense for our system, run its measurement routine, and then dispatch a function to the GPU. And so this is what I mean when I'm talking about like a dispatch seam. And then over on the GPU, we've already loaded this sort of decode operation where maybe where we have instantiated this like some sort of dispatch handler that can, with very low latency and low jitter, execute this decode function and give us a result back that we want. And so in terms of the actual implementation here, there are many ways that you could implement a paradigm like this. And so one paradigm that has gained a lot of traction across the quantum community is to use MLIR for situations like this. And so just a thought at this, there could be a path to standardization there if we have this sort of type of heterogeneous workflow, and we define dialects that different vendors, different providers can lower down to a layer that's compatible with their hardware. And this could be sort of a step towards I've heard some visions like from Jack Langier, how we have this sort of any-to-any quantum to classical tooling where we could pick and choose what's our quantum, what's our classical, and defining interfaces at this level could bring us there. If you're looking for MLIR implementation approaches, we have like Munich Quantum Toolkit in Penny Lane. They're open source implementations of these sorts of workflows. I know that was present in the openQSE archive survey, and so it's probably not a surprise to a lot of people here. For those of you at Oak Ridge, Seong Lee has some really interesting work here that I'm told is soon to be published. But I think that there are some promising things that we could do with MLIR that could be sort of an opt-in thing with vendors that could allow end users to really leverage a real-time heterogeneous kernel. And so with that, that's actually all I have prepared today. And so thanks so much to everyone for listening. If anyone has any questions or comments, I'd love to discuss.
Yeah, so I have a question. Does your pipeline provide access to mid-circuit measurement and conditional operation for this heterogeneous compilation?
Right, and so right now for sort of an end user, that's not something. Well, so I guess there's sort of two different things. So there's mid-circuit measurement, which we could, which you can describe in this interface in sort of like a circuit type interface. It's the heterogeneous part that right now for an end user would be implicit. And I think this is something that is not something we've made public yet, partially because we don't have a good way to for others to sort of describe that workflow in a sustainable way. You could do all of this in something like in like a chasm circuit, or even you could just describe it all in a quantum circuit. But that's maybe a little bit less tractable given the degrees of freedom that we have. Does that answer your question?
Yeah, partially. But I have a second question on real-time decoder and A general comment about neutral atom quantum computing that it's been described that is a slow clock frequency at the physical layer allows it's less kind of burden for real-time decoders. But that's with respect to latency. Actually, it's more of a challenging throughput if you consider you want to do parallel transversal operation. It's not that simple to execute and leverage the full capabilities of this system. Because the space-time volume of conditional operation, now we are talking about mid-second measurement and conditional operation for real-time decoding. It would be harder to compile this in real time if you want to keep the transversal operation and that versus more of a sequential. Therefore, to capture full parallelism, you need to do a little bit more than faster qubits to just compensate for the slow physical clock cycles. I'm referring to some of the Quera's proposal for transversal operation.
Sure, yeah. And so, yeah, I would say, yeah, it's a bit of a simplification. There are challenges to neutral atoms in our modality. There are a lot of things we can parallelize. There are some things that are trickier, as you rightfully point out. But yeah, I think that maybe in terms of speaking to how we address that particular challenge, I'm actually not the best person to be answering that question.
Okay, thanks.
Sure.
Maybe just quickly following up on that, do you have a sense of what class of QLDPC codes you expect to be able to support? There's lots of interesting development in this area, and in particular, I think as you get more and more complex LDPC codes, we also need to be mindful of the decoding requirements of that, and kind of just dovetailing what Masood was saying.
Yeah, I think that's right. And so I know that we have a lot of parallel efforts into different classes of QLDPC codes, and I'm sorry that I can't exactly describe what it is or what our direction is there for what sort of things that we would support. I could talk a little bit more about how we make that. How we can make things as efficient as possible, bring down latencies on the hardware side. But I think that, yeah, sorry, I'm also not the right person to speak to our direction with the QLDPC family.
No worries. Yeah, I assume it's some class of hypergraph product codes and so on, but never mind. Just was curious. Thank you.
Maybe I just like kind of go a little bit higher level. So you mentioned there are two modes, the real time and the batch time. The batch time you said is in the tens of minutes. In your experience, I guess I'm trying to differentiate between the idea of co-location and co-allocation. So, you can have the system beside your HPC or your classical, but you can also have it co-allocated. So you have the HPC and the quantum there at the same time. And for some of the things that are within the 10 minutes, do you see a need for having both the HPC and the quantum allocated at the same time? Because it will cost too much to, release the HPC and then go forward and try to, queue on the quantum, and then once that's done, they have to reacquire the HPC, which can go on a longer queue as well. So have you looked at that, or are there applications that you have explored that need this co-allocation paradigm?
Right. Yeah. And so I do think that co-location, if we're just looking at sort of latencies of links and how long it takes to store some data and pull it down, then it doesn't look like a very attractive proposition to have something like co-location. But you are right that there could be some infrastructural reasons why co-location would make a lot of sense, and why we could have some sort of, if we did have co-located quantum and classical HPC system, that it really would make sense that we could have some tightly coupled orchestration in some way to make sure that we own the resources that we need when we need to own them. That's where something that's where something like what's being proposed in openQSE, as I understand it, would be much more preferable over something like a bracket or going through one of those interfaces. So I do think that there is a benefit for scheduling.
We have a question says for the batch time workflows, are you using any workflow management systems or similar software as part of your stack?
And so we do have, as part of SuperStack, we do have some workflow management systems, but those are not something that sort of the user typically has access to. But certainly one of the things that we're strongly considering is adding compatibility with our layer to like the QRMI type interface, allowing sort of these HPC orchestration softwares to be able to interact with our systems. And so that's something that we don't have today, is some sort of like workflow management software, but is something that we do intend to adopt, and that we want to adopt an interface that allows end users to use their workflow management systems that they're used to, probably for HPC applications.
So I was wondering if you have like a few examples of quantum algorithms that you need real-time workflow on the order of a millisecond.
Yeah, sure. And so I think there's so obviously there's decoding and error correction. Quantum error correction is an obvious one, but I mean there are also workflows where it could be helpful to be in the loop. An example, if you are, say, you're the quantum algorithm designer, one thing could be like a continue until success condition or something, right? Like maybe if you are in the loop tightly, you can say continue running until I've met some success criterion, or just fail if we have met some unwarranted condition. Let's bail out early and not waste any more machine time on this problem that won't converge for me, or something like that. So I think that there's probably practical use cases for the end user where they could practically use real-time, the real-time in the loop interface.
But these are the both examples you provided are related to quantum error correction and error mitigation. Repeat until success kind of strategies are considered to me as like a error mitigation strategy, but I was more referring to algorithmic, like at the logical layer that you actually compute. It's a quantum classical co-processing.
Right.
Because at HPE we are looking at a few examples, but I want to see if you have others.
Right. And so I actually did intend that to mean as part of your quantum algorithm as well. And so, yeah, that can be an error mitigation strategy. But it could be that you want to do these tournament rounds and you want to do them as quickly as possible, and you would be able to have some mechanism to tell if you're going to be successful or something like that. That it may be useful to have hooks in there to be able to sort of see the state of your experiment.
Okay, thanks.
It will be useful because I had a comment along the same lines. It will be useful, not necessarily in this talk, but like have if you guys already are looking at specific algorithms that do require this tight in the loop classical HPC beside decoding, it'll be nice to kind of know about them in the future. If you can send me this and I can share it around, that will be nice.
Sure. Yeah. And I think that given that we have this sort of flexibility, that this is something that we expect to take advantage of and use this low-level interface in creative ways to find solutions at sort of our applications layer. And so that's the type of thing that I expect we will oftentimes be making publicly available.
Maybe I'll make a quick comment on the repeat until success circuits. That yes, it's definitely used for error mitigation techniques, but and including things like partially fault tolerant quantum computation. But what ends up happening is there's definitely a class of papers and resource estimates out there where one just assumes that the Clifford plus T synthesis requires some X resources, assuming repeat until success, So even the T counts for some of these things assumes that you have access to repeat until success circuits. And people have some arguments that on average you need to do order 1 repetitions, but that's a claim of the mean and not the variance, right? Occasionally it may be, I don't know, 10 repetitions and so on. So I think in general, a lot of these repeat until success circuits either need to be addressed carefully as like a subroutine, or we need to do a bit of de-randomization of these things and just have explicit circuits that address them.
And maybe could you speak when you say specific circuits that address it? Do you mean like we should have we should be explicitly defining that in primitives in some way?
Yes, exactly. So you either define it as a primitive that you're like an end user can say that, okay, this is what I'm expecting to use when I submit this job, or when you report the resource estimates, you don't report this on average thing, but let's say you also have you have a good sense of how many. Okay, maybe I rephrase it. You should not report the repeat until success estimated T counts. You have to de-randomize it and give an explicit error. Okay, this is your epsilon error in your Clifford plus T compilation, and this is what the circuit looks like.
Okay, thank you.
Yuri, you want to go ahead?
Yeah. Would you mind going to the slide where you had the Rocky connection? I think there was like one before this one, or
I'm sorry, what connection?
The Rocky or the RDMA over convergent Ethernet, right? So there was like a diagram of the real time and the classical.
Yeah, sure.
I think this one. Thanks. Could you tell a bit about sort of the abstraction? So I'm assuming kind of the bank of CPU and FPGAs is for your real-time quantum control pieces. That this makes sense, but what abstraction do you use? What libraries, and what can you tell a bit more about how we use it? And is it really Rocky that goes to NVIDIA, or is it NVIDIA Link? and
Mhm.
what abstractions you use to program your internal CPU FPGAs to the outside world.
Great, yeah. And so we have a stack that allows us to describe these, this real-time CPU playback and any sort of like GPU playback. And so really right now we are mostly, we're fairly focused on NVQLink here, going to NVIDIA GPUs. And that's since that's a very public part of our systems and some of our systems that we are delivering in the very near term. But so I think we could, so NVQLink to NVIDIA, I think the argument that I was trying to make here is that we could find a way to, like any given vendor could sort of define their seams, how we transfer across these different classical systems, and that for the ROS or Rocky, I've always heard it as ROS, and so maybe I'm wrong here, but the Rocky interface that paradigm, just this remote DMA, is something that we could extend to sort of any sort of classical computation accelerator, and that we could have a similar, that if we have some sort of heterogeneous kernel, that we could define some sort of similar paradigm where we're dispatching some operation over this interface to some other compute system. Does that answer your question?
No, that's great, right? So obviously everyone is trying to explore NVLink, and in your embedded environment for the CPU FPGA complex, right? You have some ability to do RDMA over one of those technologies, and it sort of is beyond kind of a GPU and NVLink like application. I'm sure maybe Amir is following up with some more erudite questions. Yeah, thank you.
Yeah, I have a follow-up. So these, like you have on the, I guess, the left-hand side of the slide, you have these connection between the different CPU FPGAs. So is the idea here you're going to perform some QPU measurements or QPU operations, and then forward the result of those are forwarded over Rocky to the GPU for decoding? And if that's the case, I guess just like a detailed question is, are you using some standardized libraries for your Rocky interface, like, I don't know, libfabric or UCX or something like that? Or are you writing,
Great. And so in terms of having all these different subsystems, I think maybe what I'm trying to, or all of these different SoC systems here, I think what I'm trying to maybe illustrate here is sort of the way that we think that our real-time hardware architecture is pretty scalable, in that these FPGAs are very tightly coupled, right? That sort of to the system, we can almost it can almost think that it's one giant FPGA with a bunch of processors on it, because we can couple them so tightly. And so doing something like, suppose that we wanted to support a TPU cluster, that we could have another Rocky link. We could probably just have another FPGA system that's tightly coupled to this other distributed network of FPGAs. And when that measurement comes in over the wire, it would be very low overhead to distribute that to another FPGA that could either dispatch something over on a GPU or dispatch it over to some other like classical compute infrastructure. And so in terms of our Rocky link, there's a few different implementation components, and some are things that we would, so at sort of like the media access, like the MAC level, This would be where we're using like vendor IPs. Currently for RDMA, because we want to, I guess maybe for our implementation might be interesting to know that we want to mostly be able to do this entirely from the FPGA fabric so that we don't have to ever really have a processor block our operations while we're waiting. And so this is pretty much entirely done in the FPGA fabric. A measurement comes in and maybe that processor can take a look at that measurement data that we just got, but it will also tee off and dispatch over to another system. And so for that right now, for the NVLink, they certainly want to make it as easy as possible for people to get up and running. And so they have what's called the hollow link layer, which is you can build the NVLink layer on top of, but implements a lot of the RDMA, a lot of the Rocky TCP/IP stack that you need to do that. And so there are some components that we have developed ourselves, including sort of this higher layer packetization stuff to format our data in a way that we can dispatch and send data over to the GPU. And then we're using their system that implements a lot of the ROS and third-party components for the MAC layer.
Sounds good. And just to clarify, all this implementation on your side is happening on the FPGA. So all the actual transfer of data over Rocky is FPGA based.
Right. Yeah. And so it'd be something like it would be something, yeah, like the CPU could probably can like tell the FPGA to do it, but we want to keep the FPGA out of the loop. I think it's very helpful for us to have this all in the programmable logic layer where we're never going to see any jitter. We're never going to, if we have the throughput once, we probably have it for every single shot.
Sounds good. Thank you. Any other questions or comments? Sounds good. Thank you, Ryan, for your time and for the